Insulation has been widely used in many industrial applications such as the steel pipelines in the oil and gas industry, thermal barrier coatings for aircraft engines or gas turbines. Due to aging and cyclic process, many hidden defects exist under insulation, such as corrosion and delamination. The insulation must be replaced when the depth of delamination exceeds the critical level. If not immediately detected and repaired, such flaws could lead to catastrophic failure.
This research project is about detecting the size of defects under coatings. The inspection system in the industry with microwave NDT is used to detect the defects without contacting the product. However, the reflected microwave signal did not show a good result for the shape and depth of defects with acceptable accuracy. We cannot know accurately how big the defect and how much is need to patch or rework. Therefore, the problem of the microwave non-destructive testing in identifying defects should be solved by increase the accuracy in predicting the size of defects. This research is aimed to study the existing deep learning-based algorithms utilized for defect detection, to enhance the deep learning algorithm on defect detection using hyperparameters tuning approach for microwave technique, to compare the enhanced deep learning algorithm against the employed algorithm on defect detection in terms of accuracy, precision, recall and F1 score. There are 5 steps in the process, which are preprocessing and labeling, feature extraction, training, testing and hyperparameter tuning. Complex reflection coefficients from the microwave signal with 101 frequency points at each inspected location are converted into a 3D matrix. Each inspected point of the sample is labeled 0 and 1 as defect-free and defect respectively. After that, both 3D matrix and label data are separated into 2 subsample sets, which are training set and testing set. Next, the one-dimensional signal is represented in the 2-dimensional array for each single inspection location using continuous wavelet transform. Each 2D array is a feature of the signal. Then, CNN is implemented for data training with 3 convolutional layers, each with 30 filters, kernel size of 2, 3 batch normalization layers, 2 max pooling layers, and followed by a fully connected layer. ReLU and softmax are chosen as the activation function for 3 convolutional layers and the fully connected layer respectively. Then, train the model on the labeled set for training, the input set for training. For the testing process, the training network is evaluated with testing set and the defect size is detected. A confusion matrix is obtained using the actual data and predicted data. Precision, recall and F1 score are also computed. To improve the performance, the CNN is enhanced using hyperparameter tuning. The number of hidden layers and the number of filters are selected, which influence the network performance. The dropout rate and learning rate are involved in the training process. The number of hidden layers is set in a range from 2 hidden layers to 4 hidden layers. The number of filters is set as 16, 30, 32 and 64 filters. The dropout rate is set in a range from a minimum value of 0.0 to maximum value of 0.5 with a step of 0.05. A set of values for learning rate is determined as 0.01, 0.001 and 0.0001. Cross-validation is used to overcome the overfitting model. The optimal model is retrained with k-folds cross-validation where k equals 3. A random search tuner is used for hyperparameters optimization to get an optimal combination of hyperparameters. After tuning, the model is evaluated again with the optimal hyperparameters. So, the result of employed CNN shows 90% accuracy and F1 score is 83.6%. The result of employed CNN after tuning shows 94.7% accuracy and F1 score is 87.2%. The confusion matrix before tuning shows 78% for defect-free and 12% for defective. On the other hand, the confusion matrix after tuning shows 86% for defect-free and 9% defective. This is the comparison between the estimated defect size before tuning, after tuning and actual defect size. This is the comparison between the estimated defect size before tuning, after tuning and actual defect size on line 7. This research also found that the performance of a model modified using hyperparameter tuning is greatly improved, but it will have an overfitting issue. So tuning alone is not enough, hence we need to solve the overfitting issue. This project can benefit the aviation, oil and gas industry, especially in detecting defects more accurately in factories and sites where consistent and detailed inspections are difficult and expensive to carry out.